Hello everyone, my name is Ruiwen. Today I'm going to present our recent work on weakly supervised semantic segmentation, leveraging the class activation map. This work is done during my master's study at the University of Toronto, together with my co-authors. This work is supervised by Professor Scott Sander. I will first introduce the necessary background and then present our method that refines CAM using transformer attention weights. Semantic segmentation is a fundamental computer vision task that assigns each pixel a class label. Deep learning-based approaches can achieve superior performance on this task. However, they require an enormous amount of training data with pixel-level class labels, which is costly and expensive. Weakly supervised semantic segmentation intends to train a semantic segmentation model with weak supervision, such as bounding boxes, points, or image-level class labels. Our work particularly focuses on weak supervision with image-level class labels. Here we show the typical pipeline of weakly supervised semantic segmentation with image-level class labels. Firstly, we train an image classification model. Then we obtain class activation map from the classifier. And we generate the initial seed area leveraging the localization ability of the class activation map. After that, we expand the seed area with some post-processing technique and use it as a pseudo ground truth label. Finally, we train a semantic segmentation model with the pseudo ground truth labels in a fully supervised manner. Clearly, the performance of the final semantic segmentation model mostly depends on the quality of the pseudo ground truth labels. And the localization ability of CAM is the key factor in generating high-quality pseudo ground truth labels. Let me briefly cover the class activation map, a common technique to identify the regions that a convolutional neural network is looking at while classifying an image. Given a trained convolutional neural network, it takes an input image and a target label. The class activation map is generated by linearly combining the feature map activations related to the target class. The method can roughly localize the objects in an image, which is extremely useful for the weakly supervised semantic segmentation task with image-level class labels. However, a well-known problem of the CAM is that it only highlights the most discriminative part of an object, instead of the entire object area. This limits the quality of the pseudo ground truth labels. Recent work has pointed out the main cause of this issue is that the local receptive field of the convolutional neural network only captures small range feature dependencies. In contrast to CNN, Vision Transformer is a recently proposed network architecture that captures long-range feature dependencies. The Vision Transformer splits the input image into patches and linearly projects them into patch embeddings. The ability to capture long-range feature dependencies comes from the multi-head self-attention module, which fuses information from all patch tokens based on the calculated attention weights. We hope this feature of the Vision Transformer can reduce the partial activation problem of CAM. Our method TransCAM leverages the conformer architecture, which is a variant of the transformer network to capture both global and local features. It can obtain CAM with more extensive coverage. And furthermore, we find that the patch-wise affinity captured by the attention weights of the transformer can be used to refine the class activation map effectively. This figure shows an overview of our method. The yellow parts represents the dual-branch conformer network. It consists of a convolution branch and a transformer branch. The representations from the two branches are fused through the feature coupling units. Our method first obtains the class activation map MC from the convolution branch. We find this class activation map has more extensive coverage compared to others obtained from the CNN backbones that were used previously. Then we refine the CAM with the attention map. The attention map is constructed by averaging the multi-head self-attention weights from all transformer blocks and excluding the class tokens. We observe that the attention map captures both low and high level feature affinities. The refined CAM has substantially improved object coverage. Overall, our method is very simple. It doesn't need to change the loss function or add additional network components. Despite its simplicity, it still achieves competitive performance with other state-of-the-art methods. We visualize the attention weights of a chosen reference point, which is with respect to a single row in the attention map. We find that the attention weights in shallow blocks mainly capture low-level local feature affinities. For example, it highlights the vests with the same color and texture as the reference point in the first row. And it highlights the black parts of the cat, similar to the color of the reference point in the second row. On the other hand, attention weights in deeper blocks mainly capture high-level semantic similarities. For example, it highlights all three persons in the first row, and it highlights the eyes of the cat in the second row. We can also see that the attention weights in deep blocks looks noisy, possibly because the patch embeddings in deep layers contain complex high-level semantic information. However, when we average attention weights in all blocks, it is able to capture both low and high-level feature affinities, while reducing the noise that comes from the deep layers. We test our method on the PASCAL VOC 2012 dataset. The first table shows the conformer architecture generates better class activation map for pseudo ground truth labels compared to other CNN models. The second table shows our attention-based refinement substantially improves the class activation map. And also it shows the averaging attention weights in all blocks for the attention map has the best performance compared to averaging only shallow or deep layers. Our method has very good performance that is competitive with other state-of-the-art methods. We obtain 69.3 in terms of MIOU on the PASCAL validation set and 69.6 on the PASCAL test set. The qualitative result on the right shows that TransCAM performs well on some hard examples where multiple objects are presented in an image. In summary, we proposed a transformer-based solution, TransCAM, for weakly supervised semantic segmentation to address the partial activation limitation of CAM due to the inherent deficiencies of CNN's local receptive field. Our method explicitly utilizes the inherent attention weights from the transformer branch of the conformer to improve the CAM generated from the CNN branch. It is based on our observation that the attention weights capture both low-level and high-level spatial feature affinities. Our method is simple and does not rely on any additional components or complex calculations. Our method achieves competitive performance for weakly supervised semantic segmentation on the PASCAL VOC 2012 datasets with the image level annotations. We have published the code on GitHub, and the full version of our paper is available on arXiv. If you are interested in our work, please make sure to check our GitHub repo and the full paper. Thank you for your interest and attention.